Alright, hello everyone. In our last episode, we introduced the photoelectric effect, and today we're going to be interpreting some experimental data. So let's recall our equation. The maximum kinetic energy of the photoelectrons is equal to the energy of the incoming light minus the work function of the material. And if we recall that the energy of the photons in this case is hf, then this looks like a linear relationship with h as the gradient, f as the variable, and negative w as the vertical intercept. So you'll see why I've prepared some axes over here. On the vertical axis, we're going to put the kinetic energy. On the horizontal axis, we're going to put the frequency. And a typical graph of the kinetic energy versus the frequency might look something like this. And the reason the graph stops at this point, if I call it f0, hopefully you'll be able to remember that there was a minimum frequency less than which would not allow any electrons to cross the circuit. And we called that the threshold frequency. So even though the graph does stop at this point, if we extend a straight line over to the vertical axis, this could be the negative of the work function. So we'll call this minus w. Because h over here is a constant and we're taking h as the gradient, that means that every experiment will produce a parallel set of results. So this could be another photoelectric effect experiment, and all we've done is change the work function. Maybe this is called w dash. So the lines will be parallel, but their vertical intercept and their threshold frequency are going to be different. Remember, the definition of the work function is that it's h times f0, the threshold frequency. So if I change the material, not only will I change what the y-intercept looks like, but I'll change what the x-intercept looks like. And I'm calling them x and y because hopefully that's something you're a little more familiar with. You might remember that we stuck an ammeter in the circuit, so instead of measuring the kinetic energy of the electrons and the frequency of the light that we use, we might measure the current through the circuit and the voltage that we're applying in the opposite direction to stop the photocurrent. And if we do that, we'll get a situation like we have down the bottom of the screen. So in this graph we have red, which is our so-called original experiment, and then we're going to change the parameters, we're going to change the frequency of light that we use, we're going to change the intensity of the light that we use, and we're going to change the voltage that we apply, or the stopping voltage, and we're going to see what happens. So if red is our original graph, we're going to compare it with our orange, purple, and green graphs. So remember, this left-hand tail is the stopping voltage, or V0, and every graph might have a different V0. That's fine. Now you'll notice that I've left the units off this graph, and I've done that purposely, because the choice of units really comes from this h over here. I could use the h that goes with electron volts, or the h that goes with joules. So if I'm using electron volts, then the kinetic energy is just V0. If I'm using joules, I need to multiply this by Q, the charge on one electron. So I'll put this Q in brackets, because sometimes we need it, sometimes we don't. So let's look at the orange one first, or number 2. You'll notice that the left-hand tail stops at a different spot than the original red graph. And that's because this one has a different stopping voltage, or V0. Its stopping voltage is less, or it's closer to 0. So this should really be the stopping voltage. So our stopping voltage for the orange graph is going to be less than our original. But it looks as though our graph will eventually catch up to our original, which means the intensity of the light is exactly the same. Remember, the intensity is directly proportional to the current. Because light is behaving as a particle, there's a one-to-one correspondence of photons coming in with electrons going out. So I'm going to write that the intensity here is the same because the number of photons coming in must be the same if the photocurrent's the same. If our stopping voltage is less, that must mean that our frequency is also less. And we can demonstrate that by coming back to our equation. If we're lowering our frequency over here, that means we must be lowering the voltage that we need to stop the flow of electrons. Now let's look at our purple graph. In this case, the stopping voltage is the same as our original experiment, and as we just talked about, that means we're using the same frequency of light. The difference between our purple and red experiment is the current coming in, and that means that we're using a lower intensity of light, because again, there's a one-to-one correspondence between the light coming in and the current flowing through the circuit. If there's less current, we must be using a lower intensity light. And finally, we come to our green, number 4 experiment. We have a lower stopping voltage. If we have a lower stopping voltage, that must mean we have a lower frequency, and the amount of current flowing through is also much less than our original circuit. And I just realized I was supposed to be writing lower, not less. Sue me. But hopefully this has increased your understanding about the different parameters that we could change in this experiment and how that would affect your data. Now beware that there are all sorts of exam questions related to this topic, and they usually have to do with people collecting data of their own and trying to estimate Planck's constant. Now Planck's constant, we've said, is the gradient of this line, which means no matter what your experiment is, you must take the rise over run between 2 points and calculate the gradient that way, not use Planck's constant that's given to you, because you're being asked an experimental question. Alright, thank you for watching everybody. This has just been a part 2 video to our photoelectric effect explanation. Hopefully you got something out of it, and remember, if you have any STEM related questions, feel free to email us or drop us a comment below.